So a function, as a definition, it's a mapping of inputs to outputs. So a mapping is just saying, okay, I'm going to take my number 2 and let's say I'm going to put it and say it goes to 4. And I'm going to take a number to number 7 and I'm going to say that has to go through to number -2. So a quadratic function, it did that. We had a lot of things going on. We had a lot of numbers flying around, but we took a lot of numbers, put it into our function, and we got a result. But in order for a mapping to be a function, there's a very specific quality that is needed to be met, and that's every member of the domain maps to exactly one output, or every number that I'm starting with doesn't get mapped to 2 other places. So I wouldn't map 2 to, okay, 2 can go to 4, and also 2 can go to -7. That is no longer a function. So to see that in practice, a few more definitions before we see it in practice. Domain is the set of all possible inputs for a function, so all of the numbers I could throw into a function. And the range is all of the possible outputs I could get from my function. Now we get to see this in practice. So this is one way to represent a mapping, or more specifically a function. And basically all it's saying is these are points. So my point 1 is my x is 1, my y is 3. My x is 4, my y is 5. My x is 4, my y is -6. Now the question we have to ask ourselves, is this a function? Because it is a mapping. I'm telling all of my inputs to go to something. But am I meeting that second part of my function? Well, if I look at it, I have 2 repeating inputs. I have 2 4s. And one of them goes to 5, and one of them goes to -6, which I'm not allowed to do by the definition of a function, so that is not a function. To see another example, I have my mapping here. I have -2 goes to -2, 4 goes to 5, -3 goes to 5 as well. And I might think, okay, well, I know in the last example there was the repeating 4, which was bad. And in this example, the repeating 5, which is bad. But what's kind of weird about the definition of functions is I'm actually not concerned about my outputs. So I could have everything mapped to the same number. That's okay. I just can't have one number mapped to 2 separate locations. So even though 4 goes to 5 and -3 goes to 5, this does meet the definition of a function. And then the question asks, if it is a function, what's my domain? My domain is my set of all possible inputs. So in this case, my domain is -3, -2, and 4. And those are found by just looking at those x values of those 3 points. And I guess I asked for range as well. And then my range is all of my outputs, so that's -2 and 5. Notice how the 5 is repeating. You don't repeat stuff if you are writing something in the range. You only need to write it once. Now this is kind of a strange case, so if this one kind of messes with your mind, don't be concerned about it. Really make sure that part A and part B make sense, but part C is kind of interesting. So again, you kind of leap out and you say, oh, okay, well, I know that having 2 input functions is usually pretty bad. That's what broke the definition of a function in part A, and that's certainly what's happening here. But it's doing something tricky. Yes, we have 2 separate inputs, or repeated inputs. We have -2 and -2, but they're actually being mapped to the same output. So even though it doesn't seem like it's a function, those -2 to 1 and -2 to 1 is actually just being redundant. And the truth of the matter is no matter what, you're taking your -1, you're mapping it to a single output of 1. So it is a trick question. It is a function. So my domain is -2 and 4, and my range is 1 and 3. Now, there's a lot of ways to represent functions. You can see it in that notation that I just write with points. You don't honestly see that too often in mathematics, but what you do see more often is tables, and you certainly see much more often equations. So let's look at tables as though they're functions. So this is a mapping, certainly. I have inputs. They are going to outputs. Now I have to see if it's a function. Well, I want to avoid having 2 inputs being mapped to the different outputs, having the same input mapped to different outputs. So in this case, I look at my inputs and I see 2, 3, 4, 7. So I have no repeated inputs. So I don't have to really be worried about an input being mapped to 2 separate outputs. So it's a function. That's kind of the nice case. If you see no repeats, don't overthink it. It's a function. Now here we have repeated inputs. We have 1 and we have 1. Well, the first one is going to 3. The second one is going to 4. So I am mapping, that circle should be on the next one. So 1 is mapped to 3 and 1 is mapped to 4. So that is not a function. Again, to be clear, 3, 7 should not be circled. 1, 4 should be circled. Now, function notation. So sometimes we only have one function, and it's almost silly to kind of say, okay, I need to be careful about how I name my functions. Like, if you are just drawing one line of a graph, there are no other equations, just y equals, I don't know, something like 2x plus 3. But quite often we deal with a lot of functions, and that's why this function notation comes about, is we want to be able to describe different types of functions, and then we want to say, okay, I'm going to use this one, and I want to use this type of output. And so that's why this comes about. It's just a way to name things. And so this example says, let's say you have your first 3 scores on your test, 87, 72, and 91, and you want to write a symbolic rule for your average over 4 tests. So even if you didn't know function notation, you would probably say, okay, average, I add up my numbers, and since I have 4 of them, I divide by 4. So 87 plus 72 plus 91 plus whatever you want to call your variable. You don't really know what your last test is. I said it was S. You could have said it was X. That's perfectly fine. And it's all over 4. But I want to be able to name this function. And so I'm going to name it A for average. And my input, since I have an S in my function, that is going to be my input. So that's what that little guy tells you. So the outside, the big capital letter tells you the name of the function. Whatever is inside the parentheses tells you what the input of the function will be. So quite often the most common function that we see is f of x. But it doesn't always have to be x. So it could be, in this case, a of s. You could have multiple inputs, in which case you should probably put a comma between them. But that's really what's happening, is we're naming the function, and then we're saying, this is the input that I'm going to be dealing with. This is the variable that will be changing. And so I've kind of already said it a couple of times. But how you would say that is a of s. So you would say the name of the function, then you say of, and then you would say your input. So anytime you hear f of x or a of s, that's what we're talking about. We're talking about the function notation. Now, if I was asked to find the average of what you got, find out the average if you got a 94% on the last test, well, that's a very long-winded way of saying my input is 94. And so I'm really trying to find what A of 94 is. So notice how my S is gone now, and I've replaced it with what my result was. My final test was my 94%. And so really that left side is we're not doing any math on the left side. All we're saying is we use the function A and we plugged in 94 in for my input. But notice how the right side of the equation, the S is gone and now has been replaced by 94. And so then we just do some basic order of operations, and we see that A of 94 is equal to 86. I didn't mention, but I should mention, one of the most common mistakes I see with this function notation, and it completely makes sense, I get why it happens, is that when we see that A of 94 is equal to 86, quite often our brain goes into overdrive and we think, okay, I can't stop there. I have to get A by itself because I'm looking for my average. That's just a name of the function. So your answer is 86. Your average on all 4 of these tests is 86 or 86%. So don't overthink it. If you see A of 94 and you have your function, that's really just telling you what to do. Your answer is just that 86. So here's the function right here. Q of P is equal to 4P minus 5. This question doesn't really have a long-winded word application and tests flying around or anything like that, but that's perfectly fine. If you're asked to find Q of 7 and you're dealing with functions, you should think, okay, well, I have to locate which function is Q. I only have one, so that's easy in this case. And then I'm going to plug in 7 for my input. So I'm going to replace my p with 7. I'm going to multiply that out. I'm going to subtract, and I'm left with q of 7 is equal to 23. And again, it bears repeating. I don't divide both sides by 7. That's my answer. Q of 0, well, I take 0, plug it in for p, solve. 4 times 0 is 0, subtract 5, I get negative 5. Now be careful with this one. So this question isn't asking you to find a value of a function. It's instead asking for you to find your input given that your output is 11. So I know that the result of my function will be 11. I don't know what my input will be. So what I do in this case is I replace my q of p with 11, and I go about solving for p. That's just fairly basic algebra. I add 5 to both sides, divide both sides by 4. I get p is equal to 4. Okay, the difference quotient. Now this is probably the most famous equation in calculus. So if you plan on taking calculus at some point in the future, make sure you feel pretty comfortable with this concept, because you'll have to do it definitely a few times, at least as far as an introduction to what a derivative is. And so if we're asked to find the difference quotient, we have to find it for a specific function. So you have to be given a function. So here we're given f of x is equal to 4x minus 5. And now I'm looking at my difference quotient. I need a couple things. I need my f of x. Well, I already have that. That's great. I need my f of x plus h. I'm going to have to find that. And then h is just a variable, so I don't really have to find h. So in order to build that difference quotient, now I'm going to have to find f of x plus h. Well, I do that. With function notation, f of x plus h means that I'm going to take my function f of x, and I'm going to plug in x plus h into the x. I'm going to plug it into the input. So when finding f of x plus h, notice how it's almost the exact same equation, except for instead of having a single x like I have for f of x, now I have f x plus h replacing that x entirely. And then once you've done that, then you have to do a little bit of simplification. And yeah, the simplification get a little bit more complicated than this problem, but as far as the process goes, that's the idea. You take your function, you replace your x with x plus h, ideally in parentheses, and then you simplify. So that's my f of x plus h for this. My f of x is already given to me, so I don't really have to find that at all. And now I just put those into my difference quotient. So f of x plus h is now replaced with what I found, 4x plus 4h minus 5. And f of x is replaced with what I was already given, 4x minus 5. Now it's a very good idea to put that function in parentheses because we're subtracting every time we do the difference quotient. And so we're going to want to make sure that we distribute that negative sign to both things inside my function. So I'm going to do that. So all that does is it becomes a minus 4x and then a plus 5. And now I simplify as far as possible. So my 4x's will cancel out, my 5's will cancel out. And now here's a very important step, or at least an important checkpoint along the way. So one of the cool things about the difference quotient is that if you are doing all of your steps correctly, your h's will always cancel out. So if you get to this step in the process and you have a 4h plus a 6 flying around at the end and you can't really cancel out all your h's, you did something wrong. There's a good chance you flipped a negative sign. That's usually the issue. But that's super nice to be able to say, oh, actually, that's not how this equation should break down. Let me go back and see where I made my mistake. And so my 4h over h becomes 4 because my h's will cancel out. And that is the difference quotient. Here are the definitions, which seem a little bit overwhelming, and maybe you feel like you have to memorize them. It's not really true. We're just posting these definitions to say, okay, if I'm adding functions, what I'm able to do is actually just look at the individual functions and then add them together. Or if I'm subtracting entire functions, well, I can look at individual parts and subtract them. So I wouldn't worry about memorizing these, or if you're prepping a note card for the future to study with or something like that, focus less on these and more on the actual problems. So for example, we're going to dive into, I'm given a function f of x and I'm given a function g of x, and I want to find f minus g of x. And it makes perfectly logical sense, but technically without the definition above, I wouldn't be able to just write each part and subtract them. But that's exactly what I'm going to do here. So I'm going to write each part and subtract the individual functions. So f of x is 2x plus 1, and I'm subtracting g of x. And just like I mentioned in the last section, when you're subtracting, make sure you're putting your entire function in parentheses. Otherwise, you're probably not going to distribute the negative correctly. So that's what I did here. So my next step is to distribute that negative correctly. My x squared becomes negative x squared. My 4x becomes negative 4x. And then I just combine like terms. And that's my answer, negative x squared minus 2x plus 1. That's going to happen a lot. Usually when we think about algebra, we think, oh, I'm going to get an answer for x. I'm going to get a number or a fraction or something like that. If we're dealing with adding or subtracting or multiplying actual functions, and you see a g of x or f minus g of x, you're going to have an x in your final answer, so don't kind of panic with that. But if I have a very similar question with a 3 there as opposed to an x there, now what I'm going to do is I'm going to plug in 3 for each individual function. So I plug in 3 into my f of x. Well, that's 7. 2 times 3 is 6, plus 1 is 7. And then I plug in 3 into my g of x function, and I simplify. Well, 3 squared is 9. 4 times 3 is 12. Add them together, the bottom cut it off, but it is 21. G of 3 is equal to 21. And now I just take those individual pieces and subtract them. F minus g of 3 is the same thing as f of 3 minus g of 3. I have both of those values, 7 minus 21, and I get negative 14. Now, you have two options when you have a number involved. One of your options, and in this case it's very doable, is to plug the number into each individual function and then perform the addition or subtraction. Or if you really wanted to, we already had f minus g of x above. And what I could do is I could plug in 3 into that result that I found in part A, and then we'd get the same answer. So it's one of those that, yeah, quite often it is easier to kind of find the parts and then get the final number, but sometimes you might have already found the function, or sometimes finding the function or adding or subtracting the individual functions isn't so hard, so you want to do that first and then plug in. Either way is fine. So I believe we've talked about domain before, worth revisiting, very important concept. There's really 3 cases of domain. The first case is if we have x in the denominator, and so the process for solving that is we set the denominator equal to 0 and we solve. So I have my function here, I set the bottom equal to 0, I solved, and now my domain is everything but that number. So it's negative infinity up to 5 and 5 up to infinity in interval notation. Next one is if we have a square root that has an x inside it, we set the square root of whatever's under the square root greater than or equal to 0 and then solve. And so in this case, x is less than or equal to 2, which with the domain gets me negative infinity up to 2. And then the third case is pretty much everything else. That's the domain, that's all real numbers.